All right. All right, now let's get back to trusses. We just talked about stability and determinacy of trusses. Let's move on to solving the, analyzing them and solving for their forces. There are two different methods that you can use, and you don't have to use them each exclusively. You can use them together, but we're going to learn them separately. There are two different methods to analyzing trusses. One is the method of joints, and one is the method of sections. So the method of joints is if you determine your member forces and reactions only by looking at each individual joint. So I'm going to look at each individual joint and solve for equilibrium. Earlier we talked about they can only have tension or compression, the individual members. How do you determine which ones are in tension and which ones are in compression? There's two different methods of doing that. So two different approaches to determine tension or compression. I guess tension or compression member forces, right? That's what I'm talking about. You can either assume everything's in tension and find out that it's not, or you can make a guess and see if you're right. Basically. One, always assume every member is in tension. And if it comes out negative, that means it's in compression. Or two, make an educated guess. And if you're wrong, the sign will change. So either assume everything is in tension or just guess. And if you're wrong, either way, well, you'll figure it out because your sign will change. So how would I draw the member forces? Let's say I have this little triangular truss here. I'm going to break it up into 3 different joints and 3 different members. Right. If I call this A, B, and C, if I look at, first, if I want to assume everything's in tension, I gotta draw it in tension. And then if I want to know the direction of the forces on the joint, like say at A, I just do equal and opposite, right? Equal and opposite. So you can see not only is the tension pulling on my member, but it's then pulling on my joint. Similarly, equal and opposite over at B, and then equal and opposite over at C. If they were in compression, like let's say this member was in compression, my forces, if I'm drawing the vectors, would look like that. Now that member is in compression, and the force on the joint by the member is equal or opposite. So, as they always say, draw pictures. Makes you understand a little bit better. So, picture is worth 1,000 words. And I think I've already said that before, so I'll try to stop saying that. But it's true in engineering, right? We like equations and we like pictures. We don't so much like the words. So this is how we analyze a truss using the member. This is the approach using the method of joints. If we want to write down a specific procedure, first draw a free body diagram of a joint. If you want to solve for the forces at that joint, you need to make sure there's at least one known, with at least one known force and at most 2 unknown forces. So I'm going to select a joint that has at least one known force and at most, like at least one known force and at most 2 unknowns. Why at most 2? Because I only have 2 equations of equilibrium. Some of the forces in the X and some of the forces in the Y. If this was a space truss, a 3D truss, I could have a third unknown force because I'd have some of the forces in the Z. But we're sticking to 2D, so. And I need to have something known, because if I have nothing known, then I can't solve for anything, right? If I don't know anything, I can't use my knowledge to solve for the unknowns. So be strategic in choosing a joint to start with. You can then choose an approach for determining tension and compression. And this again can change as you go along your structure. If you're like, well, I really think this one's in compression, then draw it in compression. Don't just say I'm going to assume tension and make the math prove you otherwise. You can pick one, and as long as you're consistent, the numbers will tell you if you're right or not. Then solve for equilibrium at that joint. Right, I have my two equations, some of the forces in the x and some of the forces in the y are both equal to 0. And then continue around the joint for all the joints in the structure until you know all you want to know. Right? Right? Start with one joint, solve for equilibrium, move to another joint, solve for equilibrium. Keep going until you know all the member forces and all the reactions. So let's do an example. Here's my little triangular truss subjected to a 500 Newton force at joint B. My first step is to look at the reactions, right? So at A, it's a pin, so I have a vertical reaction and a horizontal reaction. C is a roller, so I only have a vertical reaction. You can probably from this conclude what RAX is, but let's pretend. So I'm going to start with B. Actually, I could start with A, but let's start with B. Let's start with A here. And we'll see why we can't start with it. You've probably figured it out by now. But let's look at equilibrium at A. So let's see. Here's joint A. It has member AB going vertical, member AC going horizontal. If I assume everything is in tension, I have a horizontal force in member AC. I have a vertical force in member AB. I have a reaction in the X direction and a reaction in the Y direction at A. right? Just looking at this one right here. So, how many forces do I know? None. How many forces? Right? Oh wait, no, how many? That was how many unknowns I have. How many knowns do I have? None. Unknowns, 4. I need to have at least one known, and I need to have at most 2 unknowns, so this ain't gonna work, right? So I can't solve yet. Alright. So let's go look at B. Let's see. There's my joint. I got member AB vertically and member BC diagonally. I have an applied load of, if you can see it, an applied load of 500 newtons. A force in AB and a force in BC. How many knowns do I have? I have one known, right? That 500 Newton is a known force. How many unknowns? 2. I can solve using equilibrium, right? I have at least one known and at most 2 unknowns. So I can solve for equilibrium at joint B. So, gonna redraw that. I have equilibrium at B. My force in member BC, my force in member AB. I can change my force in BC to components. FBC Y, FBC X. And let's solve for equilibrium, right? Sum of the forces in the X direction, assuming right is positive, is 0. I have 500 newtons acting to the right. And I have the horizontal component of member BC. Well, right away you can realize, even though I chose it to be in tension, it's going to be in compression, right? FBCX equals negative 500 newtons. It's a 45-degree angle, so this is a 45-degree angle. So FBCX is FBC, right? If this is 45 degrees, of course it's 45 degrees, so it doesn't matter if you really use sine or cosine, but you know, FBC times sine 45 degrees. My force in member FBC is negative 500 newtons divided by sine 45 degrees. Break out your calculators. You should get negative 707 newtons. Oops. Now I can solve for the sum of the forces in the y direction. I'm going to assume up is positive. That looks terrible. Positive. My two vertical forces are force in member AB acting down. And then the force BCY acting down. Right now we're gonna add that negative back in there, but right is 0 if FBCY is FBC times cosine 45 degrees, right? This is my vertical component. So it's cosine 45 degrees. FAB equals, can make this positive, but now it's negative. Negative FBCY, which was negative 707 newtons. Cosine 45 degrees. So get out your calculators. She got 500 newtons. So my force in BC ended up negative. That means it's in compression. My force in AB ended up positive, and since I assumed it was tension and it was positive, then it is in tension. Right? So force BC is 707 newtons compression. Force AB, oh geez, is 500 newtons in tension. That looks terrible. So, I don't know if that made it even better. 500, oh my lord. Unselect 500 newtons in tension. So all I did was solve for equilibrium at B, because I could do that because I had one known force and two unknown forces. Now I'm going to move on to joint C, right? I just figured out that this has 707 newtons compression. This one has 500 newtons in tension. Now I'm going to look at equilibrium at C. All right, so I'm going to look at my joint. I have member BC coming up at a 45-degree angle, member AB, which is horizontal. Then I also have that reaction, right? It's compression, so I have 707 newtons compression coming from member BC. I don't know what's going on with AB or with AC, so I'm just going to assume it's tension. And I'm going to assume that my reaction is up. I have, let's see. How many knowns do I have? One, I know 707 newtons. Number of unknowns is 2, that force in AC, and the reaction at C. I should have written a C there. Reaction at C. So I can use equilibrium. Now, what if I went back to A right now, right? Let's see. A, I didn't know the two reactions, and I didn't know force in AB. I didn't know the two reactions, and I didn't know the force in AB or the force in AC. By solving for equilibrium at B, I know FAB now, but I still have three unknowns. I don't know the reactions, the vertical or horizontal components, and I don't know the force in member AC. So I'm going to come back to equilibrium at A later. So I'm sticking with equilibrium at C, right? Some of the forces in the X direction is 0. I have the horizontal component of my force at BC, right? And I know that's acting in that direction. And then in the opposite direction, FAC, my force in member AC. So force in AC is force, the horizontal component of the force in BCX, which is 707 newtons times, right, if that's 45 degrees, the cosine of 45. So FAC is 500 newtons. You see it's still positive, so it's in tension, because I assumed it was in tension and it came out positive. Just pausing for a moment. Then if I do the sum of the forces in the y direction, assuming up is positive, I've got the vertical component of FBC acting downward. And I have the reaction at C acting upward. RCY is the vertical component of the force at BC. So that's FBC times sine 45. Oopsies. So my reaction at C, my vertical reaction is 707 newtons times the sine of 45 degrees. Maybe have figured out by now that's 500 newtons up, right? Okay, so I solved for my two unknowns, and now I'm going to go back. The only thing that I don't know, let's see, I know that this is 707 newtons in compression. This has a horizontal or vertical component of 500 newtons. This is 500 newtons. In tension. This is 500 newtons in tension. It's very hard to write vertically. 500. What I don't know now, I only have two unknowns, the vertical reaction and the horizontal reaction at A. So for completeness, let's do equilibrium at A. Let's see, here's my joint. I have the horizontal member AC, the vertical member AB. They both have 500 newtons of tension, one horizontal, one vertical. No diagonals, so I don't have to deal with sines and cosines. If I assume that's up, you can see it's probably not. If I assume that's to the right, you can see it's probably not. But you know, this is where you can make your own decision. You can just be like, you know what, I think it goes the other way. And draw it the other way. But let's just pretend that everything stays that way. So let's see, I only have two unknowns, and I have at least one known. So now I can solve using equilibrium. I'm going to solve for the sum of the forces in the x direction. I have RAX plus 500 newtons equals 0. So RAX, my horizontal reaction at A, is equal to negative 500 newtons. That means it's to the left. And if I sum for the forces in the y direction, assuming up is positive, I have my vertical reaction at A and my force in member AB. And I get that my force in my vertical reaction is actually down. All right. So you could write RAY equals 500 newtons down. Actually, X 500 newtons to the left. RAY is 500 newtons. So what is your final product? You draw your structure. And you write in the member forces, which is 707 newtons in compression, 500 newtons in tension, 500 newtons in tension. I'll add my load on there. My reactions are 500 newtons down, 500 newtons to the right, left, and 500 newtons up, right? And you should also probably write A, B, C. And there you go. That is solving a simple 3-member truss using the method of joints.